Welcome to the Agilent video training series. In this video, we will review image pre-processing in the Gen5 software, where we specifically explain how to process your images for uneven background intensity. For image microscopy, correcting for uneven background is crucial. The traditional method of background correction involves manually measuring and subtracting the fluorescent intensity of the background from the objects of interest. While this approach can be effective, it introduces variability due to factors such as differences in background intensity between samples, dye properties, variations in fluorescence expression, and other variables. A more objective and consistent method for correcting background intensity is the use of the rolling ball algorithm. The rolling ball algorithm works by correcting for background intensity and smoothing out uneven illumination. For example, in the matrix shown on the screen, each square represents a theoretical pixel, and you can clearly see the uneven background. The algorithm places a ball over the image and calculates the average pixel intensity within the ball. It then rolls the ball across the entire image, updating the intensity at each position. This process generates the background map, which represents the calculated values. Once the background values are quantified, they are subtracted from the original image to remove the uneven background signal, resulting in a smoother final image. As the user, the main thing you need to consider is, what size should my rolling ball be for my sample? A good rule of thumb for 2D monolayer fluorescent cell cultures is to make the rolling ball 2 to 5 times larger than your object of interest. For example, if the object is a nucleus with the size of 20 microns, the rolling ball should be set between 40 and 100 microns. This range generally corrects for any uneven background signal found in the image. In the image on the left, the line profile tool displays the fluorescent intensity across the nucleus and the surrounding background. When the rolling ball is applied at the appropriate size, it flattens the background, allowing the fluorescent intensity profile to focus more on the nucleus while reducing background noise. If the rolling ball is too small, it can delete pixels and erase important data. If it's too large, it may not effectively correct for uneven background signal, and it will take longer to process the images without any noticeable benefit. While starting with a 2 to 5 times larger ball is a good baseline, the exact size depends on the specific characteristics of your sample. Certain samples, like 3D thick samples or label-free bright field, may require special adjustments. Our software also includes default settings based on the objective size to give you a good starting point. This image clearly demonstrates how the rolling ball algorithm can improve data processing. When the rolling ball was set to twice the size of the mitochondria stained with TMRM, the mitochondria became sharper, which allows for more accurate segmentation during analysis. Let's review how to set up the image pre-processing step in our software. In the matrix on the screen, you'll find images captured from a 96-well plate. To create a protocol to image a microplate, please refer back to Converting from Manual Mode to Experiment Mode video. You'll start by clicking on one of the images for a closer view. Before processing, you will want to estimate the size of the objects. In this example, there are 3 different objects: a nuclei labeled in the DAPI channel, the cytoplasm labeled with a cytosolic GFP protein in the GFP channel, and the cytoskeleton labeled with an actin marker in the red channel. You'll now obtain the size of the nuclei and cells. Using the ruler, the estimated size of the nuclei is approximately 20 microns. While the length is not the exact size of the nuclei, it is a close enough approximation for determining the size of the rolling ball. Next is to estimate the size of the cells. In the GFP channel, the estimated size of the cell is 60 microns. The red channel will be similar, as both markers label the entire cell. You can simply delete the rulers if you do not want it in the image. Next, click on the Process button at the top of the window. From there, choose Image Pre-processing and click OK. This window will allow the user to adjust the diameter of the rolling ball. By default, the system will provide recommended values based on the objective size, which typically works well. However, you can manually adjust these settings based on the object size. There are other functions available, such as image smoothing strength and priority speed, but these will be covered in more detail later and are rarely necessary for background correction. For the DAPI channel, Auto will be unselected and rolling ball size will be set to 40 microns, approximately twice the size of the nuclei. For the GFP and Red channel, the Use Same Options as Channel 1 will be unselected, and the rolling ball size will be set approximately twice the size of the cells, which was 120 microns. As you can see, the image is much crisper and sharper. Now, a common question that comes up is, what should my rolling ball size be if some wells contain smaller cells due to assay design, such as assays that kill or shrink cells? The key is to base the rolling ball size on your larger, healthier cells. If the rolling ball is set too small, it could lead to pixel loss, as we saw earlier with the nuclei example. Now select Add Step. Gen5 is now applying the rolling ball to each individual well. To toggle between the raw and processed images, simply select the window in the top left corner. The default naming, TSF, stands for Transformed. From here, you can apply additional processing steps or analyze the images, which will be covered in our other training videos. When you select the calculator icon at the top of the toolbar, it will open the data reduction window. This window displays any processing or analysis steps that have been added to the protocol. You'll notice that image processing is included in the protocol. When saving the experiment or the file as a protocol, the image processing step will be automatically included, and the software will process the images after imaging the next plate. This concludes our training video on image pre-processing. In this video, we walked through the setup process in our software and provided general guidance on setting the rolling ball. Ultimately, it is up to the user to determine the optimal settings for their specific sample types. Thank you for watching, and don't forget to explore other topics in our training series.